The universe undeniably expanded, endlessly stretching out further and further. After a certain period it continued to grow, but at a slower rate, eventually reaching the universe we know today. This concept is part of the inflationary theory, which is the most well-known and widely accepted explanation for how the universe began. However, for some physicists, this leading theory no longer fully explains the origin of our universe. It suggests that the universe existed before the Big Bang, continually expanding into both the past and the future. While the universe is still expanding today, it was originally contracting before the Big Bang. According to this view, the Big Bang wasn't a singular event but a transition, with the universe repeatedly contracting and expanding. Some physicists even propose that the universe may be in a perpetual cycle of expansion and contraction, eventually leading to another Big Bang in the distant future. The prevailing cosmological model suggests that the universe began with a massive explosion, but some physicists, including Brian Cox, question this notion. They argue that something can't emerge from nothing, which challenges the traditional view of the Big Bang. The James Webb Space Telescope has made some surprising discoveries that conflict with the idea that the Big Bang marked the universe's origin. These revelations have raised the question: if the Big Bang wasn't the beginning, then what was? Did the universe have a beginning at all, or has it always existed in some form? The idea that the universe may have had no true beginning dates back to 1927, when George Lemaitre proposed that the universe might have existed eternally in some form. Despite the evidence supporting the Big Bang theory, some scientists still believe that the universe could have had multiple origins. They argue that the Big Bang might not be the true starting point of all things, and that the period before the Big Bang could have been vastly different from what we know. The inflationary period that preceded the Big Bang is key to understanding the universe's early history. During this phase, the universe was nearly empty, with no particles or photons. Space itself was filled with immense energy, which gradually transformed into matter and radiation. Over time, this energy expanded rapidly, cooling down and leading to the formation of the universe as we know it. The universe continued to grow and evolve, but the rapid expansion slowed down as it approached the current state we observe. This inflationary model suggests that the universe went through various phases of expansion, each marked by changes in temperature and energy. Early on, particles behaved like radiation, and energy levels were extremely high. As the universe expanded, this energy cooled down, leading to the creation of matter. Eventually, the universe reached the state where the Big Bang occurred, marking the beginning of the universe we observe today. However, the rapid expansion continued after the Big Bang, with distant regions of the universe moving farther apart. This ongoing expansion means that areas of the universe are still stretching, and the universe continues to evolve. Some physicists propose that the universe could experience another phase of expansion, which would drastically alter the course of its evolution. As the universe expands, regions of it slow down, and the rate of expansion decreases. In some areas, expansion has already ceased, leading to the formation of new structures, while in others, expansion continues. This model suggests that different parts of the universe may experience expansion at different rates, and that regions far from us may eventually disappear from view as they stretch beyond our observable range. In this inflationary picture, the universe's expansion rate changes over time, with some areas eventually experiencing a halt in expansion. The energy in space transforms, and new matter and radiation are created. As the universe continues to expand, quantum instabilities and fluctuations emerge, creating regions of higher and lower density. These fluctuations serve as the seeds for the formation of cosmic structures, which we may not yet be able to observe. Ultimately, while we have learned much about the universe's origins, the exact nature of the universe's beginning remains elusive. The evidence provided by the James Webb Space Telescope and other tools continues to challenge our understanding, suggesting that there may be more to the universe's history than we can currently comprehend. Despite the ability to extrapolate and understand hidden density instabilities, there are inconsistencies within the cosmic microwave background (CMB) that challenge our current cosmological models. The CMB provides evidence of the universe's origins through the Big Bang, but it also presents anomalies. These inconsistencies can be summarized in 4 key areas. First, on large scales, the universe is not behaving as expected. The light from the CMB is being lensed through space, meaning it acts like a giant lens, bending and distorting the light's amplitude. This lensing effect is not always predictable according to our leading cosmological models. Additionally, the CMB shows temperature discrepancies, particularly along the equator of the CMB sky, conflicting with the assumption that the universe began in a uniform state. Second, the Hubble constant, which describes the rate at which the universe is expanding, shows discrepancies depending on whether it is measured from the CMB or from nearby stars. These inconsistencies suggest that our interpretation of the universe may be missing something important. One possible explanation for these anomalies comes from loop quantum cosmology, which arises from loop quantum gravity. In this framework, gravity itself is made up of particles called quanta, forming the fabric of spacetime. According to this theory, the universe cannot have originated from an infinitely dense point, as the Big Bang theory suggests. Instead, the universe might have emerged from a quantum bounce, where a contracting universe eventually expanded again, similar to a phoenix rising from the ashes. This idea, while not entirely new, is supported by a mathematical structure in loop quantum cosmology that addresses many of the cosmic anomalies observed, particularly the temperature variations in the CMB sky. If loop quantum cosmology is correct, the early universe may have had a soft energy and density that influenced the CMB's temperature variations, providing strong evidence of the universe's origins. This model offers a potential resolution to the inconsistencies in the CMB and could explain the differences in temperature between different regions of the CMB sky. Furthermore, the idea that the universe began from a big bounce rather than a singular beginning is increasingly being explored. However, challenges remain, particularly regarding entropy, which increases with each cycle in cyclic cosmology. This suggests that the universe would become increasingly disordered with each cycle, potentially contradicting the idea of an eternal universe. The widely accepted inflationary model, which describes the rapid expansion of the universe following the Big Bang, is still the leading theory. However, some physicists argue that it doesn't fully capture the universe's development. They propose that the universe existed before the Big Bang, continuously expanding and contracting. In this view, the Big Bang was not a singular event but a transition moment, where a contracting universe began expanding again. This cyclical model avoids the need for a singular beginning, suggesting that the universe could continue to evolve indefinitely. Yet, this hypothesis faces challenges, particularly in reconciling the increase in entropy with the idea of a continuous universe. Brian Cox, a prominent physicist, challenges the notion that something can emerge from nothing, questioning the traditional view of the Big Bang as the origin of all matter. Recent discoveries from the James Webb Space Telescope further complicate the idea that the Big Bang marks the universe's true beginning. These findings raise the question: if the Big Bang wasn't the start, what was? The concept of the universe having a beginning was first proposed by George Lemaitre in 1927, but proving that the universe had a clear starting point is difficult. Much of the history of the universe prior to the hot Big Bang that shaped our observable universe is still uncertain. Many astronomers still believe in the Big Bang as the origin, but the idea of a non-singular beginning is gaining traction. Evidence increasingly points toward a universe that didn't have a single origin tied to extreme temperatures or densities. Instead, the universe likely underwent an inflationary period before the Big Bang. The Big Bang represents the end of this inflationary stage, when the universe transitioned from a state filled with energy and radiation to one with matter and light. As the universe continued to expand, its energy spread out, slowing over time and leading to the observable changes in the cosmos. These changes, while initially rapid, eventually slowed to a pace that allowed the universe to reach its current state.